Okay, so thanks for the introduction. So it's always great to come back to the Implementor's workshop. It feels like a bit joined in a guilty pleasure with like-minded people, with a lot of like-minded people. So I will be presenting. So that's me, Haskell. I will be presenting the work here, which was actually done mainly by Malak Al-Chabri, a PhD student of Philip and myself, talking about multi-level Haskell implementations. And in short, the topic of the title is how to make your current programs run on a cluster without changing your current sources at all. So that's the main goal of what we are doing. Is mainly work on the runtime system, working on Haskell language level. So we started. So our motivation for doing that entire work is that we are Haskell hackers, runtime system hackers, and we don't want that. Of course, the politically correct motivation is, if you look around, what are the most commonly available card processing platform nowadays, what you find are clusters of multicore machines. So they are in just about any institution. You can easily get access to them, and you get a lot of cores with them. But how do you program these machines? Well, what's nowadays often used is something like OpenMPI and OpenMP on one shared memory machine, and MPI on top of that in order to link the individual nodes together. So you get two different concepts of doing parallel programming. That's a burden to the programmer. Moreover, using MPI on the top level, so doing explicit message passing between nodes, is a very low-level way of doing programming. It's very error-prone if you've ever tried that. So we want to get away from that programming model. And what we want to do is we want to give the programmer a higher level of abstraction in order to do that programming. So that's kind of a simple picture of the machines that we want to program, but actually many of these cores, as many as possible ideally. And as a programming model, we want to get away from this low-level programming. So what is our language? So the language that you see as a user is nothing new. It has been around for quite some time. It's Glasgow Parallel Haskell. So it's a small extension to standard Haskell, which only requires you to identify parallelism in your code. So if you have your parallel Haskell program, what you do ideally is just you take a highlight pen, you look at it, and you highlight the expressions that you have in your program that you want to be executed in parallel. That's the basic idea. We call it semi-explicit because all the synchronization that needs to happen, all the communication that needs to happen with the network is done automatically in the runtime. And that's what we are focusing on. So this is more or less just a reminder of the language that I'm putting up here. So we have just one primitive. So par does this highlighting. Par highlights the first par as being potentially parallel. We call that in our jargon sparking parallelism, because we just store a point that's fairly lightweight in order to do that. What we use in practice are then evaluation strategies, which are an abstraction over this primitive to make the parallel programming simpler. So this is a standard example. So this is how you define parmap in GPH. You say parmap behaves exactly like a map. So the result value is just the result of a map over the list here. Moreover, you apply this strategy to the evaluation once it's kicked off. And the strategy here, parlist, encodes that you want to do each of the function calls in parallel. Okay? So you separate here the computation from the coordination, which is an important feature, and that's the style of programming that you get. So it's mainly intended for purely functional, stateless code in your programming language to be minimally intrusive. That's one of the main design goals. It's one of the parallel Haskell extensions. You can read up more on that. So we have a summary in a summer school that we ran recently at Harriet Watt, if you want to look up the details, or look up the Haskell standard papers for more details on the language as such. So now let's move on to the runtime system, which is what we are mainly interested in. In the bigger picture, there are several runtime systems which implement this language model that I've just shown you. So the first one is GUMSMP. So GUMSMP is the shared memory implementation, so which works on physical shared memory machines. So you get it with the standard GHC distribution, so you can start using that on your multicore, basically without any changes to the system. You just download the strategies or the parallel module in order to get these kind of parlist constructs. If if you want to use them. So that's very easy to get to. You exploit all the cores on one machine, which is great. You can do it on server-style machines today, so that's quite substantial. However, what the system doesn't give you automatically is the network connection. Okay? So if you want to do it on a network as well, you basically, you need to program it on top of the application. You don't get it baked into the runtime system. So that's the monitor. The second implementation that you can get is GUM. So that's our research platform in order to do parallel computing over distributed memory architectures. The design of GUM was from the start for networks, so you get a configuration like this, but initially for single core networks. So that was our traditional setup, large clusters of single core machines in this kind of configuration, where the runtime system internally sends messages between the different nodes in order to exchange data. So MPI is used, but it's used inside the runtime system, and you as a user actually don't see it. You probably just see it when you configure the system because it asks for an MPI library. But that's all that's needed. The new system, so the main one that I'm talking about today, is a merge of these two functionalities. So GUMSMP, as the name indicates, is a combination of shared memory and distributed memory parallelism combined in one system. So you run one instance of the SMP runtime system on one multicore, and on top of that, you use one layer of GUM in order to glue all the different things together. So this GUM layer will do the message passing for you, and we build on the existing technologies in order to get the combination together. So we get a couple of advantages out of this combination. But first of all, this gives you the opportunity to use entire clusters of multicores rather than just one cluster, which is a big advantage, and which means that you get scalable parallelism over that cluster. You add machines to it, and you hopefully get better performance out of it. And we use the cheap way of managing parallelism that you can do in the physical shared memory machine. So we build on the tuned version of the SMP system on a physical shared memory machine in order to achieve high performance there. Now, to go into the technical parts of things, the way how we achieve this large-scale distribution is that we implement a virtual shared memory abstraction in the GUM layer of the runtime system. So we keep track on, so logically what's happening is just graph reduction on a logically shared heap. So nothing changes from that point of view, but internally we keep track on which node is one particular closure residing on, and we automatically exchange messages if we need data on this. So we have implicit synchronization if data that's needed is not yet evaluated, with implicit blocking, and we do on-demand communication, on-demand message sending, and packing of structures at the point, and just at the point where they are needed in the computation. So we maintain the laziness in our language by doing this on demand. One focus of our research is automatic load balancing. So how do we distribute the work on the cluster in order to improve performance? And I'll talk more about this. And we still have a single programming model, which I think is a big benefit if you compare to other approaches to parallel programming on clusters that you find nowadays. Okay? So the main part will be about work distribution. So let me jump to the slide where we discuss work distribution for GUMSMP, for the combined system. So we have here several nodes, each node with 3 cores executing a distributed program in our scenario. So there are 2 different work distribution mechanisms. So if you're, for example, in that situation and one particular core on this multicore runs out of work, so this here is just representing the CPU. This part here represents the spark pool. So this is just a collection, a set of all potential parallelism that we've identified through par annotations. It's mainly a set of pointers that we have here, so nothing table-based. So each core has logically associated to it a spark pool. If one of the cores runs out of work, well, in the physical shared memory model, it's fairly easy. You can just go through the spark pool, check whether there's work available in any of the other spark pools. You grab one of these pieces of work, and you execute it on your own core in order to continue with work. So typically we grab some work from, so this is actually a queue that's used here for representing stuff. You usually pick something from the beginning of the queue in order to get something large to execute. So that's the picture within one multicore, direct access to sparks that are available in the physical shared memory. And that spark moves over, and that will go ahead and evaluate the graph structure. If we are on a node like this one, where we don't have any local work available at all, the system will go to the other spark pools, check each spark pools for work. It will detect there is no work, so it will delegate to the scheduler and send what we call a fish message to a different processor. So a fish message is just a work request. It will be sent around through the network. It will be forwarded if there's no work at that particular machine. Here, we immediately find work that's available. So we identify one particular spark. We pack the graph structure, so the subgraph underneath that closure that is referred to. It is sent away through a schedule message to the other processor, and that will go ahead and just merrily reduce the graph structure that has arrived from a different processor. So that's the basic model of doing graph reduction in the distributed context. So these are kind of some baseline performance numbers, some speed up graphs that we have from our usual suspects of benchmarks, starting from very simple perfect-like benchmarks, which give quite good speed up, to some of the more interesting benchmarks like Minimax, so an AI search algorithm, and Maze, another search algorithm encoding speculative terrorism in it. And what we see a range of speedups here, so quite good ones for the simple programs. For some of the other programs, so we measure it up to 100 cores. We use a cluster of 8 core machines, scaling it to 100 cores in total for these measurements. We do get decent performance here, but a flattening out early on, so about 40 or 50 cores in the execution. So our main goal is to basically bump up the speed up that we get here, and in particular improve the load balance that we have in the program. So try to spread out the sparks as evenly as possible in order to keep all of them busy during the execution of the program. This basically is the same picture, just scaling it to higher core numbers for the programs where we did the measurements. So we do run it on up to 180 cores. Roughly the picture is the same as in the previous picture, so these ones still scale very nicely. So yeah?
Is that a parfait with a sequential bottom out, or?
Yes, so it has a thresholding included in it in order to tune the performance. So as I said, it's fairly minimal to identify terrorism. You can then do some performance tuning using techniques like thresholding to throttle the amount of terrorism. And we had a paper in FHPC how to do that in Haskell more flexibly than just thresholding, or do chunking in the program. That's usually encoded in strategies that you attach to the program. Okay, so what we want to do is improve the work distribution. So that's one of the main goals. When you go to a large cluster, it's not trivial to keep all of the programs busy, irrespective on what program is running. So we want generic procedures to do that. So what we've done, we've introduced watermarks in our model of a spark pool. And a fairly simple idea. So this is the spark pool holding all potential parallelism in the program. We introduce a low watermark, which means that we always want at least that many sparks available in our spark pool at any time in the computation. That means we actually start doing some prefetching of work, although we are not sure whether we need it, which is departing from the usual picture, purely on-demand request for works. The high watermark then has the semantics, if we exceed this, then we actively offload work to another processor. So if we have a lot of parallelism, we push it away, even though we are not sure whether other processors actually need some work. So that's more drastic because that moves from the default passive load distribution that we do normally to active load distribution. We mainly use the low watermark in the performance measurements that I'm showing here. So that's the main idea, to have a bit more control about how work is distributed, do some prefetching of work in order to have it available at the point where we need it. This is one snapshot of a load balance profile, a PRPE profile of one execution where we don't use low watermarks. So what we show here is on the y-axis the nodes that we have available in our cluster. 16 nodes in total, and I think we use 5 cores on each node, so it's an 8-core execution. X is the runtime. What you see in the picture is the amount of runnable threads at any point in the execution shown as a green value. Red means there are none, so that's idle time, so that's something that we want to get rid of. But also note that processor 1 here has a very dark green value, which means it has a high number of runnable threads available. The others are only lightly loaded, so light green values, which means it's fairly uneven load balance if you do this without our low watermark mechanism. Contrast this with the load balance picture that we get when we enable low watermarks. So we now use that mechanism to more evenly distribute the work, and you see it's darker green throughout the computation. So first of all, most of the red parts have disappeared, which is good, well, except for this one. The load is more evenly balanced most of the time in the system, so that works well in this particular snapshot that we have shown. It's not perfect. I mean, you see that we have red areas at the end here. So this indicates that it's beneficial to switch the policies throughout the computation. At this point, the main DE has a couple of threads available, but there is a low watermark which prevents from moving away work, sending it out to other processes. So you might want to switch, for example, to a different policy, depending on what's going on in the system, and that's one active direction of work that we're looking to monitor execution and adapt our policies that we normally set for one entire execution. But by and large, low watermarks are a winner. So the runtime here is actually dropped by around 60%. So they are scaled to the same picture. So if you look at the speedup graphs and compare the unticked versions without low watermarks with the ticked versions, like these ones here, that use low watermarks, that's actually an improvement for all of the programs that we have tried on the entire range of application benchmarks. For the small ones, as shown here, and also on the larger ones, which have flattening out, it bumps basically the picture, the speedup graph, and improves scalability on larger clusters. So low watermarks are a clear win. So we have that now set as a default in our distributed runtime system in order to improve work distribution. And we're still working on dynamically managing the policies, which is one important future work. Another thing that I want to mention is to improve data locality. So by and large, the big challenge that we find in doing distributed computation in this model is have good work balance or load balance, and also have good data locality. Keep the data that's needed for a thread with that thread, and don't just send it away to a different process. And the basic idea here is to introduce something that we call spark segregation. So in the basic GUM model, all sparks are equal. So there's no difference between a locally created spark. So you might, for example here, a thread might be running creating sparks. That would be a locally created spark for the process. But there are also global sparks, so sparks that have been sent from one processor to a different one, so that come from another processor, which, when be turned into a thread, are likely to engage in communication as well. So our intuition, therefore, is we would like to prefer local sparks where possible in order to keep the data together, to avoid too much communication in the system, and only when there is no local work available, we resort to global sparks. And that's implemented by introducing an import spark pool, which is an additional spark pool that holds these global sparks and that we just use when we are run out of local work. Okay. So the goal here is good data locality, or in other words, tackling heap fragmentation in our system, which is one aspect that we have observed before. Heap fragmentation is in general an issue with any kind of virtual shared memory system. So it's basically, intuitively, it's the scenario where related data structures that are needed for the same computation are on different nodes, which means you need to communicate in order to get that data. We want to keep that aspect, heap fragmentation, down in our system, and fortunately we have a way to measure this. This is a snapshot on what's happening when you do communication, so details are not so important, but just notice what we need anyway is a table that connects the globally unique identifier that we have for communicated closures with any local closure. So that, for example, is a link between a globally unique identifier, and a local closure that has been transferred from this processor to this processor. So that's basically the processor before communication, the processor sending, and this is the processor receiving the graph structure. The point I'm making here is we already have this table in our system. We just measure the size of the table in order to get a metric for the heap fragmentation that exists in one particular program. And in our current work, with the import Spark code, what we are trying to do is to get this its table size down, reduce heap fragmentation, and thereby reduce the communication and improve runtime in our system. That's ongoing work. We have some improvements in terms of table size, so roughly reduction of 11% in the table size, which is a starting point. I mean, I was hoping actually for larger reductions, but that's really new, just implemented by Mara a few weeks ago, and she's currently working on measuring this on the entire range of benchmark programs. So the main goal is improving the data locality in our system, which is another major block of work. Okay, yes, I will skip over this part and just summarizing the conclusions. Yeah. Let me go on to the conclusions. So, GUMSMP, so the main aspect of GUMSMP, it combines shared memory and distributed memory parallelism in one system using the same language model that you're used to when you do shared memory programming with Haskell and NV. And you can run it on networks of clusters. The main benefits that you get with GUMSMP is you get the tuned parallelism that you have for a shared memory system already. So you pick up the technology that exists, and you get a scalable model because you can grow the cluster if you get new machines and just use the same runtime system to run it on a different application. You're not restricted to a physical shared memory machine. Our main research direction is to hierarchy-aware load balancing, so get a good balance across the machine. That's one major piece of work. And also to tackle data locality in order to keep related things together and reduce communication. The main improvement that we started is a low watermark mechanism on the Spark pools, which gives us consistent improvements for old applications, up to 57%, so up to a factor of 2 faster execution on the benchmark, so that's quite substantial. And we are currently working on Spark segregation, so we have an implementation, but we're still evaluating it, and we'll have to tune that particular aspect. So we don't have performance numbers, just initial results on reduction of table sizes. Overall, in the current setup, we get speedups in the range between 40 and 135 on 180 cores. So that's quite substantial sizes of cores that you're using, and good results for some of the programs, and improving the results by improving of our runtime system for the lower end of that spectrum. And the final remark, which is the part that I skipped over, separately we've also done work using our GUMSMP system, not on a network, but using it on one shared memory machine. So you have the opportunity to basically decide how many cores should share one heap when you use a GUMSMP system. Okay? And what you can do is you can tune it so that on one shared memory machine you use as many heaps as you have NUMA regions available on the shared memory machine, avoiding one large shared heap and distributing things across several local heaps that you run on the shared memory machine. And in our measurements, we get actually performance improvements if you tune the system to several local heaps, matching one NUMA region on the shared memory machine, to improvements over the shared memory performance. That's in a separate paper. If you're interested in that line of work, get in touch with me. So we have something written up and quantified results on this in a paper that's currently under review. Our ongoing work, so that's, I didn't talk about that in detail because a sidetrack. It's, I think, in general of interest, but the main track is to improve the distributed memory performance, and the main direction is Spark segregation to improve this, and also do some message batching to keep messages together and avoid too many small messages, which is another artifact that we have in our system and can reduce performance. Okay, so thank you.
Time for one quick question. In front of you is the person.
Okay. So I would like to, because this is the one of the few applications I see for distributed system. So
Okay, great.
let me make it. So I'm using a K computer. So let me have 1,000 nodes and with hydrodynamic simulation. So you will be using after more than half of the memory to keep the arrays, and you're going to update a million times. So saving the data will be actual problem. So one node cannot contain data for two nodes. How can you manage that situation? How would you garbage collect on that situation?
Okay. Yeah, so there are two issues to mention here.
Yes.
So in terms of garbage collection, it's basically the same picture of a logically shared heap. So we do distributed garbage collection across the distributed heap, doing weighted reference counting, which means there are messages exchanged in order to detect the spot where something is not needed anymore on another processor.
You need to ask globally to detect that.
Well, it's not globally, it's basically to that actual processor. If you detect that it's no longer locally needed and you have a global pointer, you send a pointer to the other PE in order to tell this it's not needed anymore. You give back weight to that other processor in order to free the data. So it's basically weighted reference counting, specifically, that we're doing on a distributed heap. In terms of arrays, I should mention our model is tuned really for the side effect free part of Haskell. So it's best used in purely functional code in order to do the computation.
Can I use it? Can I do I/O stuff with it, though?
Well, you can do I/O stuff, but what you typically do is you have the top level I/O, the monadic part, and the parallelism is just in the functions that you call from the top level in order to get your parallelism. I mean, there are other fine Haskell models which are more of a monadic style. So if you are more in that part, you can look into that direction. So there's a good choice out there.
There's a few things I want to ask you later, but
Yeah.
Okay, we should move on.
Thanks again.